Okay, today we are going to talk about algorithms that help us to find minimum spanning trees. But first, we need to discuss what a tree is. A tree is a specific type of graph. It's a graph that is connected and doesn't have any cycles. By connected, we mean we can go from any vertex to any other vertex. If we have a disconnected graph, we can't go from any vertex, say this vertex, to this vertex because there's no path or no edge we can move along to do that transition. Also, a tree doesn't have any cycles, meaning if we start along a particular edge and we visit various vertices, as long as we don't go over the same edge twice, there's no way to go back to the starting point. Now you notice with this tree here, if we start at this edge, or if we start at this vertex, we can go along this edge. So this vertex go along this edge here and then revisit our starting point without having traversed the same edge twice. So this graph has cycles and is therefore not a tree. Now, if we have a particular graph, for instance, this is the graph we will be working with throughout this lesson, we can make lots of different spanning trees from that graph, which are trees that visit all the edges, well, trees that visit all the vertices without having cycles. Okay, so here we have 5 examples of spanning trees that are valid for this particular graph. You'll notice all of them are connected graphs, and none of them has a cycle. You'd also notice that if we have 6 vertices, which is what we have for this tree, our spanning tree will have 5 edges. If we have less than 5 edges, then there is some disconnection somewhere. And if we have more than 5 edges, then we have a cycle. So for a graph with n vertices, we will have n minus 1 edges in a spanning tree. If we have less than n minus 1, then we wouldn't have a fully connected tree. And if we have more than n minus 1, we would have a cycle somewhere. Now, we will be interested in not just any spanning tree, we will be interested in a particular type of spanning tree. We will be looking at connected undirected graphs, meaning there will be no specific direction for the connections. They are two-way connections. If edge from vertex A is connected to vertex B, then B is also connected to vertex A, and both edges have the same weight. Okay, we will be talking about weighted graphs because minimum spanning trees don't make any sense without edges having weights. Since what we're talking about the spanning tree being the minimum is that if we should draw that particular spanning tree and add the weights along all of its edges, the sum of the weights should be minimum. That's what makes it a minimum spanning tree. Now we're going to look at a particular theorem that is very useful when we want to design algorithms to construct minimum spanning trees. Now, let's T be a minimum spanning tree for a particular graph G. And let A be a subtree of that minimum spanning tree. And let the edge from vertex U and V, which we will denote as UV, let that edge be a minimum weight edge connecting the set A to every other vertex that's not within the set A. Okay, so V minus A is the set of all vertices in our graph that are not in set A. For instance, if this is our set A, everything outside of this set A is in V minus A. And what this theorem is saying is that this edge, being the minimum weight edge, is part of the minimum spanning tree. Applied to this particular diagram, if we have our set A and it's part of a minimum spanning tree, we are going to identify the minimum weight edge that goes out of this set. Now, going out of this set, we have this edge with weight 7, this edge with weight 5, this edge with weight 8, weight 2, and weight 9. Obviously, the minimum weight edge going out of this set is this edge with weight 2. And what the minimum spanning tree theorem states is that means this edge should be part of the minimum spanning tree. I am not going to go through the proof. The proof is in most textbooks, most algorithm textbooks. It's also available online. Now, let's go through the theorem again. And here we're using another example. We are taking the set A as including only this vertex B. Okay, and what the theorem states is that going out of this vertex, if we can identify the edge with minimum weight, which is this edge, then this edge has to be part of the minimum spanning tree T. And one more example, if we have A including the vertices C, F, and G, and we identify all the edges going out of this set A, we would see that the minimum weight edge is this edge with weight 1. And the theorem tells us that this edge has to be part of the minimum spanning tree. So as we go through the two algorithms, we're going to look at both Prim's algorithm and Kruskal's algorithm. We are going to see that they make use of this fact. Okay, now let's look at Prim's algorithm. Now, to understand how Prim's algorithm works, first, let's not consider the algorithm itself as written here. Let's go through the process of what the algorithm does, and then later we will relate it to what we have here. Okay? Good. Suppose we're going to start at any edge. Well, we're going to start with any vertex. Okay? Suppose we start with this vertex G. Now, we know that if we have a spanning tree, that edge has to be connected to some other edge as part of our spanning tree. Okay? Good. And the minimum spanning tree theorem that we've just looked at says that if we look at all of the edges going out of our selection, we're going to take this random selection we made of one node, We could have started with any node and we would get the same spanning tree. We're going to take this as A, and everything outside is V minus A. Okay, so we're going to look at the edges that go outside, and the minimum weight edge is this edge. So we include this edge as part of our minimum spanning tree. And what Prim's algorithm says is that we start with a random edge and then we start with a random vertex and then find an edge, and then we extend our set. Okay, so our set was originally just this vertex, and now we've extended our set to include these two vertices. Okay, so now this is our new A, this set, and V minus A is now everything outside of the set. So let's say V minus A. Now we look at all the edges going out of our set A, and the minimum edge is obviously this one. So we know that this edge is part of our minimum spanning tree. And that means we can extend our A set, and our A set now becomes, our A set now includes these three vertices. Now, going out of these three vertices, the minimum edge out of 7, 5, 4, 3, and 9 is this. So now we extend our set. Our A set now gets to include these 4 vertices. So next, we have, going out of our A set, the edges 4, 5, and 7. And the edge with the minimum weight obviously is this. Okay? So we're going to extend our set to include this. Okay? And that means this is now our A set. And going out of our A set, the minimum is this. And now we have gone through every vertex. And what we have left is this minimum spanning tree with the red edges. And we can know the total weight of the minimum spanning tree by adding these numbers along the edges. And that would be 5 and 4, which is 9, 12, 14, 15. Okay? And that's the sum of the weights along the edges. Good. Now we're going to do another example. What I'm going to do is I'm going to take this weight. I'm going to exchange these two weights. And then that will very likely give us a different minimum spanning tree. Okay, I have exchanged 7 and 4. And we're going to go through the same procedure for generating our minimum spanning tree. Okay, good. But now in explaining the procedure, I'm going to take this into consideration. I'm going to take the algorithm into consideration. What the algorithm does is we have our graph G, we have our sets of weights, and we have our starting vertex, which could be any vertex. We could start from any vertex and we should get the same weight minimum spanning tree. Okay. Now for each vertex in our graph, G dot V means the vertex set, the collection of vertices in our graph. Okay, for each vertex, we're going to set a key value as a very large number, infinity. Okay, so that it's larger than any of these weights. Okay, good. And we are going to set the predecessor. Each vertex, we're going to give a key value and a predecessor, which is what pi is. We're going to set the predecessor as nil. Now, the reason why we're keeping a predecessor value is so that we can walk through the minimum spanning tree, going from predecessor vertex to descendant vertex. Okay? We are going to set the key value of the root to 0. And we are going to make a priority queue. Now, a priority queue is a collection from which we can extract something with minimum value. Whenever we extract a value from a priority queue, what we will get would be the object that has minimum value. Okay, so what we're going to do is we're going to put all the set of vertices in our graph within the priority queue. And the way we value a vertex is by the key value we've set. But as you see in this initialization, we have set all the key values to the same value, which is infinity. Okay, so there's no way really to differentiate them, except for the key value of the root, which we've set to 0, which means when we extract min at the start, what is going to be extracted is the root. Okay, the root vertex. Now, this is where all the action happens. And what this says is, while our priority queue is not empty, while it still has vertices within it, we are going to extract the vertex with the minimum key value, which at the start would be the root vertex since we gave it a key value of 0. Okay? Now, for each vertex that is on the adjacency list of that vertex we extracted, if that vertex is still in the queue and the weight of the edge from our current vertex, which is u, to that vertex on the adjacency list is less than that vertex's key value, which at the start it will be, since all key values would be infinite. Okay, we will set the predecessor of that adjacency vertex as our current vertex, and we will set the key value of that vertex as the weight of the edge between the current vertex and that adjacent vertex. Okay? Example, suppose we set our root as G. Okay? This is our root. And then we get to line 7. We extract our root, which is G. Okay? Because it would have the minimum key value of 0. for each adjacency, now G would have as adjacencies F, C, and D. And the weights respectively for those adjacent vertices would be 9, 2, and 1. So for what I'm going to do is, so the top left of a vertex, I am going to put what its key value is, okay? Well, the key value for G would be 0 at this point. At this point, the key value for F would be infinite, okay? But since this vertex would still be in the Q and its weight would be less than the infinite value, this weight is going to be written as the new key value for this node. Similarly, this weight of 2 is going to be written as the new key value for this node. And this weight of 1 is going to be written as the new key value for this node. Okay? So we've done it for all the adjacencies for our root. And once we've done that, that is, we've gone through this for loop as many times as possible, we go back to line 6. We see that the Q is not empty. Okay? Right now, the Q has every vertex except this root vertex because we had extracted it from the Q. Okay? So we see that it's not empty, so we go to line 7 and we extract min. By extract min, we would look at all of the key values. The key values are 9, 2, and 1. Also for these other vertices, the key values would be infinite. Okay? And a priority queue, okay, we're talking about a mean priority queue. Extract min means we're going to extract the value with the minimum key value. We're going to extract the vertex with the minimum key value, which is this, since it has the minimum key value. So now U becomes this node. Okay? And for each vertex in vertex D's adjacency, which are G, C, and D, we're going to go through each of them one at a time. If V is in Q, now this will not be in the Q. Okay, it was our root and it's no longer in the Q. It's been processed. Okay, now what I'm going to do is I'm going to circle a vertex that has been processed so that we know it's no longer in the queue. Okay, so we skip this if statement for this adjacency. Then we go to this adjacency. Okay, C is in the queue. Okay, and weight of UV, that's the weight connecting C and D, is 8. It's not less than C's key value. C's key value is 2. Okay, so we don't go within the if statement. So the predecessor of C remains as G. Okay, it's not updated, and its key value is not updated as well because it's got a lower key value than this weight. Then we go here to the third adjacency and we notice that the value here is 4, B is in the Q, and 4 is less than infinity, so we set this as 4. Okay, now these two are out of the Q, so we could kind of like call them the A set at this point. Okay. Now, and this is what we used, the edge that we used. By the way, notice that in this algorithm, we are not keeping a copy of the edge. If we want to find the edge later, what we would find out is that for node D, D's predecessor would be G. Okay. Now, going out of these, okay, once we've processed all the adjacencies for D, we go back to line 6, the queue is not empty. We extract the minimum, and you'd notice the key values that we now have are 4, 2, 9, and infinity. Okay, the minimum is this. So now C is going to pop out of the priority queue. Okay,